This video is on section 3.7, which is titled Transforming to Achieve Linearity. And so in the videos, they went over transformations to linearize data. And they looked at like raising data to powers with a power model. And then they looked at using log or natural log to try to linearize a model. And so looking at the quiz doesn't focus on the power models, so I'm just focusing on the logarithms to do this video. So ultimately, if I have data and it's not linear, so I have a scatter plot and it's curved in some way, what I want to do is go through two steps. The first step is that I change the y values using log, the common log base 10 or the natural log base e. So I'm either taking the log of all the y values and graphing those new x versus log of y or x versus ln of y. And so whichever, if my scatter plot then is more linear, so if it turns into a straight line, then that tells me that the data follows an exponential model. And so the reason that it works is because if I think about taking an exponential model in the form y is approximately b to the x, and I take the log of both sides, I can use properties of logs to transform this. I get that the log of y is approximately, I've got a power rule here, so because this has an exponent, I can move it to the front of the logarithm. So y is approximately x times log of b. And so note that log of b is just a constant. So ln of y equals x times some constant. So that now is a linear function, right? So I have a variable times x equals a function of y, log. So that's going to give me why that works by creating an exponential model, just taking the log of y. If that doesn't work, so if it's still curved, then I want to go ahead and take the log or ln, so whichever one I did, of the x variable 2 and plot those points. And so that would show me a scatter plot that is more linear if the data follows a power model. So a power model, if we're talking about regression, would be y is approximately a times x to the b power. So for that one, maybe I decided to do ln of both variables. So if I take the ln of both sides of this equation and I use properties of exponents, let me give myself a little more space. I can't necessarily use the power rule right away, but I can use the product rule. So I have ln of y is approximately, because these are being multiplied inside the log, I can expand that to ln of a plus ln of x to the b power. Then I can use that power rule to move that to the front. So this gives me the equation ln of y is approximately ln of a plus b times ln of x. And so I have a variable inside a logarithm, and then ln of a is a constant and b is a constant. So I have a linear function with a slope of b essentially, and then a y-intercept of ln of a is how we can kind of look at that. It's not entirely true, but for the sake of brevity. So then they will give you problems. So first you'll see problems with scatter plots where you have to know based on what they did, what type of model. So you need to know that if there's only the ln of y or log of y, it's exponential. If there's ln or log of both x and y, that's when it's a power. So we'll ask you for that. Next, you'll see a couple things where they'll give you the output on the computer. And so if I have the computer output of a problem, they will ask me for the least squares regression line. There will be other problems that give you the least squares regression line and ask you to find a predicted value. And so I'm just going to do these in one example together so that we write the line and then we calculate the value. So for the first one, we've got water is poured into a large cone-shaped cistern. The volume of the water measured in cubic centimeters is reported at different time intervals, measured in seconds. A regression analysis was completed and is displayed in the computer output. And so they tell us volume versus time. So that means volume is our y and time is our x. Sorry, our y hat. So they gave us, remember that the constant is your y-intercept, and the time cubed is your slope. So if y hat is volume, that tells me that volume hat is equal to negative 0.013, my y-intercept, plus my slope, 0.262, times time cubed. Okay, so this shows me that they found a power model because volume is cubic, three-dimensional, and time is one-dimensional. And so they cubed the time to linearize this data. So once I've written the regression line, then I can find a predicted volume. So to find the predicted volume, I'm literally just plugging in 6 seconds for time. Okay, so I'm going to use the equation that we have in the previous problem. So volume is equal to negative 0.013 plus 0.262 times 6 cubed. Okay, so that cubed doesn't go away. I still have to cube that 6 in order to get the inaccurate output. And so if I calculate this in my calculator, that gives me a value of 56.579. And then remember, our units for volume was cubic centimeters. Okay, so using our regression line, we just have to plug in that value. The last one we're going to look at is a similar thing. It's just got a different type of equation. So data was recorded for the temperature of a cup of water, coffee, over a 30-minute period. A regression analysis was completed and the computer output is given. And so the regression analysis says that our response variable is ln of temperature versus our explanatory variable is time. So remember that when they took the common log or natural log of just one of the variables, that this then is an exponential model. Okay, so they determined that exponential was the best fit for this. Remember that this one, because we saw that exponent, that's a power. It would have also been a power if they had like log of volume and log of time. Okay, so those would be another example of a power model. So if we're writing our least squares regression line, remember that our constant is our y-intercept. So our ln of the temperature hat is equal to our constant 4.20 minus 0.023 times our response variable, which is time. So that is my least squares regression line based on that computer output. I'm going to use the least squares regression line in the next problem. So I'm going to rewrite it without the explanatory variable. So 4.2 minus 0.023, and we're gonna plug in time. So they're telling us that they wanna find the predicted temperature in degrees Celsius after 12 minutes. Okay, so if I plug in 12, I have that the natural log of the temperature hat is equal to approximately 3.924. So this is not my answer because it's not the predicted value of the temperature. I have to actually get the value of the temperature. So remember, what's happening here is that I have to use exponentiation to get rid of the ln, meaning I have to write everything with a base that's the same as the natural log. So the natural log has a base of e, so I'm going to take and raise everything to a base of e. That cancels out the natural log, they're inverses. So that means that the temperature hat is equal to e to the 3.924, which is approximately 50.6, and then our units were degrees Celsius. Remember that if you had a common log, you would exponentiate with a 10. Okay. So on most calculators, you have ln and then as a button, and then above it, it would say like e to the x or something. So you would have to hit second or shift. Same thing should be the case with log. You should have a button and then it has 10 to the x as the shift. It's a little bit easier to do 10 to the x though, because you can just type in 10 and then use your exponent button to get whichever the value is for that power. Okay, so if it was an ln, we would be using a base 10 to exponentiate in that step. So really that's all that is covered on the quiz. So a visual scatter plot for these, and then something like this where you just find the regression line, and then other problems where they give you the regression line and you have to find a predicted value.